So here we have a pretty standard linear application problem. I'm just going to read out the problem first, and then we're going to break it down to see how our linear applications or our linear skills apply to this application problem. So in the example, we have a mechanic A, which charges an initial fee of $100 plus $40 per hour of job. And then we have a mechanic B, so a separate mechanic. They charge a different initial fee of $60, but they charge a higher variable rate. I'll explain it as $50 per hour of the job. So what you can see is that we have a varying initial rate and we have a varying variable rate, I guess we could call it. And then that's going to change the value of the job depending on how long it is. And that's the key between different linear models or different linear applications. It's the fact that there's two things that control the price. It's the initial fee, or the C value in our linear equation, and then we also have the gradient, which is the variable rate. And I'll just explain why it's the variable rate with the first example, and then we'll see how it's actually being applied. But just keep in mind that when we have a linear equation, y is equal to mx plus c. We always come back to this equation, and then we try and model our linear function based on this equation here. So the first part is asking us to model the two functions of the prices. So what we need to do is figure out it hasn't actually said in this case, and it's either poorly written or it's allowing you to kind of think about it. We'll consider the latter, where it's actually allowing us to think about it. But what you should think about is what's the independent variable in this problem and what's the dependent variable. Now, based on this, you should note that the independent variable is time in hours, because you can see that the rate is $40 per hour. So what's controlling our overall price at the end of the day is the time that it takes in hours. Now, obviously you can use minutes as well, but it doesn't make sense because just hours make sense because that's how the rate is given to us. And then our dependent variable, or what we're actually tracking at the end of the day, are the prices of each of the mechanics. So that's our independent variable is time. Our dependent variable is the money, or the charge of the fee, pretty much in dollars. Okay, so let's model the two functions now. So let's just start off with A. What I'm going to do is just call it A of t, just makes sense. That's our function name. So that's going to be in dollars. So A of t, I would say I don't have to specify that A is in dollars in this case. It's pretty self-explanatory, but I should say that t is in hours because just to be clear. So again, mx plus c. So we have to think about what the m is going to be in this case and what the c is going to be in this case. I gave it away before in the way that I read it, but for mechanic A, it has an initial fee of $100. So what that means is that it doesn't matter how much time. I should change this to t, not x. mt plus c, because it's not x, it's t. Now, mt plus c. So the c value is our initial fee. Now, the $100 doesn't change it changes irrespective of how much time is spent on the job. So that's why our initial fee is going to be the y-intercept graphically, which is going to be $100. Now, if it's $40 per hour, then the m should be 40, the coefficient of t. And that makes sense because just imagine, right? If you have a 1 hour job, how much money are we spending on a variable rate? We're spending $40 plus the initial fee of $100. If it was 2 hours, it would be 40 multiplied by 2, because 2 hours, $40 per hour, it makes sense, it's going to be $80. So in this case, what it's going to be is 40t plus 100. And this overall equation is going to be representing dollars. So I'm just going to say t in hours, and maybe I'll just specify, just to be clear, AT is equal to dollars, just like that. That's not really readable, but hopefully that makes sense. Again, hopefully the equation modeling makes sense because that's the most important part of this problem. And that's why whenever I went through linear applications or just linear functions in the past, I referenced the gradient or the m value to also be considered the rate of change. So the rate of change in this case is $40 per hour because that's the rate that time essentially changes with in this case. That's how we can kind of think about it as. But just in general, you kind of don't think about it as rate of change, think about it as the rate of something. So in this case, the rate is $40 per hour, but then you have your additional $100 that's just charged on top. Now, based on this, B should be relatively easy because it's exactly the same process. You add your initial value at the end, and then you have your rate multiplied by time. So B of t is going to equal, it's a $60 initial fee, so that's at the end. And then we have $50 per hour, so it'll be 50t plus 60. And again, B of t is equal to dollars, time is equal to hours. Pretty self-explanatory. Now, part B, sketch the two models on the below axes. No axes labels here, but let's just add them in. So we'll just add time in hours it's good practice to put the unit in square brackets. That's what I've done in engineering, and I'm not sure if that's what they teach in VC methods, but I'm pretty sure they're not too picky on that type of thing. And then this is going to be dollars. And I'll just put $sign there. Okay, cool. Then what we need to do is sketch each of our equations. I might actually introduce a different color. Give me 1 sec. I'm just going off camera to get a different color here, just so we can make it really clear. We'll start off with A of t. A of t is equal to 40t plus 100. So obviously the y-intercept is 100, so we're going to start off there. I'm just going to draw it roughly, I want to leave enough space for everything else, all the other information. So I draw it roughly there. And then it's going up at $40 per hour. So let's just draw a linear equation, honestly. Just like that. Cool, nice. So I'm just going to draw this point in, 0, 100. And then let's draw B of t now. So B of t starts off at 60 as the rate, so just 60% of the height of this value here is roughly there. But then you can see that the rate is higher than the other one. So you can imagine B of t increases at a higher rate because the magnitude of the rate of change is greater. So you expect to rise up at a greater rate. And if you want to be specific, it's rising up at 10 more per hour, but it doesn't really matter because we haven't specified the t-axis yet. So what I'm actually going to do is, this is actually a really cool trick as well. I'm just going to draw a line, and I know it's going to intersect somewhere. It just makes sense because this one is rising up at a high rate. So you know there's going to be an intersection somewhere. It's not going to go downwards. It's going to go upwards and then intersect the green graph, B of t. So I know it's going to start off lower, go upwards like that, and then intersect somewhere. I'm just going to label this B of t. Now, let's just initial rate as well, 0, 60. And then don't forget this, the origin is really important as well. Just to specify, this is 0, 0. I'm just going to note down 2 different things that I've done here. The first one is that I've made my y scale smaller than my x scale. I know, like just intuitively, I know this is going to be a few hours here, just based on the numbers that I see. So this is going to be t is equal to 3, but then some people might be thinking, if this is t is equal to 3, the height is equal to 3 is like really low on that graph there because the scale is super small. Now the reason why I've done that is because the y scale is a lot bigger than the x scale. So I want to shrink down the y scale, but I still want to keep the axis itself relative. So that's why 60 is about 60% of the height of 100, and then the x axis I've done, or the x scale I've done independently. But as long as each axis is in ratio with itself, then that's fine. I don't want to keep both axes in scale because what happens is that if this height is 100 and the across is 3, I mean, it's going to be really tall, but then the x is going to be really small. So that's why I keep the axes on different scales, but each axis keeps its own scale, if that makes sense. Each axis is linear with itself. 60% of 100 there. I'm going to keep that relative throughout all my graphing. But again, x and y doesn't have to be relative to each other. It's good if it can be in situations where you have similar magnitudes of numbers, but in this case we don't have similar magnitudes, so we don't actually do that. Now, one other thing that I haven't mentioned yet is I haven't found an anchor point yet because I'm going to use the intersection as an anchor point. I know in part C, because I've already read this question, explain which mechanic is better to use. That requires me to find the intersection. That intersection is going to allow me to have enough information for both graphs. So what I'm going to do to explain which mechanic is better, now, better in this case is cheaper for the customer, so that's what I'm going to assume in this question. So you can see that there's some situations where there's a certain amount of time where one mechanic is better, there's one situation where both mechanics are the same price, and then there's one situation where one mechanic is cheaper, or the opposite mechanic is cheaper after that. You can see B of t, or the mechanic B is cheaper, and then there's an equilibrium point, you could kind of think of it as, and then after that, A of t is cheaper. So I'm going to explain that in words, but to figure out how I'm going to explain it, first I want to find that intersection by letting my two models equal each other. So what I'm going to say is that A of t is equal to B of t. I'm going to try and keep it as high as possible because it can't reach down that low. So I'm going to say 40t plus 100 is equal to 50t plus 60. And then I'm going to rearrange everything and try and solve for t. So I'm going to move this 40t to that side, and I'm going to move the 60 to that side. So 100 minus 60 is equal to 50t minus 40t, which is 10t. Therefore, t is equal to 40 divided by 10, which is equal to 4 hours. Nice. So we know that the intersection here is at 4 hours, which is what my guess kind of was. I said a few hours. And then what we do is we find the y value as well by plugging it into either function. This is kind of simultaneous equations theory that I'm not sure if it's before or after this video, but simultaneous equation theory, the y value should be same. So you could plug your x value into any equation to get the corresponding y value. It doesn't matter which one, because in theory, they should both be the same, because that's the point of simultaneous equations. A of 4 is equal to 40 multiplied by 4 plus 100, which is equal to 160 plus 100, which is $260. So we've got 4, and then we have 260 as the y value. Now, I don't want to give my full length explanation, but I'll try my best to include it all on this whiteboard. I'm just going to see how much space is on the right of this whiteboard. Oh, okay, you can see very much to the right. Hopefully there's not too much glare, but I'll give my explanation for part C here. I'll do it in dot point form as well, because I like to explain things in dot points because it saves a lot of time, and you can kind of just skip straight to what's important. Okay, a lot of people want to write big blurbs when it comes to explain questions. I'm not really like that. Dot points, one for each mark, pretty much. Now, explain which mechanic is better. So I'd say if time is less than 4 hours, then mechanic, which one's cheaper? B is cheaper. And I'll say at t is equal to 4 hours, mechanics are both same cost. And then if t is greater than 4, then A of t, or mechanic A, is cheaper. And this is pretty much a summary of which mechanic is better to use at whichever time. I've got the 3 different cases: when t is less than 4 hours, when t is equal to 4 hours, and if t is greater than 4 hours, and which one's cheaper in those scenarios. One thing that if you're writing this explanation in a test or an exam or a SAC or whatever, then one thing that I would change about this explanation is just, instead of saying t is greater than 4, I know that's the mathematical way of saying it, but maybe I'll just use the longer way of saying it. So if the time of the job is greater than 4 hours, you can write it out in words. I'm just not sure if this mathematical notation will give you the marks for explanation questions. It just kind of, I think it would on an exam, but on a SAC, all teachers mark differently. So I can't say whether or not this explanation will give you the marks with your teacher, but the only thing that you'll need to improve is just don't use the mathematical notation. Just say if the time of the job is less than 4 hours, literally in words, then that would just be a safe way of ensuring that you get the marks. That's all I'd say about this question. Hopefully you don't see this question as too difficult. I wouldn't say it's extremely difficult, but it's just a matter of doing the basics right. So what I said before, making sure that you have your endpoints and you have an anchor point, which in this case is intersection. Label your models. A lot of people forget that. Label your axes because it's going to be unlabeled in this case, and then label your origin as well. Actually, one thing that I didn't specify is the implied domain for this problem. The implied domain of this problem is, I could even specify when I created the models, I could specify for both models that t is greater than or equal to 0. And that makes sense because in this case, a job, the time of a job cannot be negative. So I'm going to specify the domain, which is t is greater than or equal to 0, and that's how I've graphed the equations as well. I haven't gone to the left of the y-axis or the dollars axis because it doesn't make sense to have negative time, but in this problem that's true. But just keep in mind that in other problems, there are rare circumstances where time can be negative. Let's say if you're talking about yesterday, that might be t is equal to -1. I've seen questions like that. So it's not a blanket statement, but for most cases, and in this case it's pretty self-explanatory, that t can only be greater than or equal to 0 for our domain.